Welcome to this explainer. Today, we're doing something a little different. We are going to totally strip away the sci-fi magic of artificial intelligence and give you a much-needed machine learning reality check. If you've ever wondered how these massive, complex models actually work, and more importantly, why they sometimes fail spectacularly, you are in the exact right place. We're going to demystify the gritty reality of AI and show you what actually goes on behind the mathematical curtain.
Imagine you're building a system right now, and your ultimate goal? To predict exactly which online videos are going to go viral next week. Now, are you going to throw the absolute most complex math at it, or are you going to focus entirely on human behavior? Well, let's dive into this, because this scenario sets up the ultimate showdown between two competing approaches in the tech world.
So, picture two completely different approaches. Strategy A, it's all about algorithm obsession. We're talking months, designing deep neural networks, crazy complex optimization tricks, the whole shebang. But then there's strategy B, and that is pure data obsession. You focus entirely on real, messy human behavior, like what people watch at 2 a.m., how trends spread like wildfire in group chats, how mood changes affect viewing habits. After rigorous experiments, something totally wild happens. Strategy B, the simpler model, almost always crushes the complex one. Why? Well, because in the real world, the main bottleneck isn't usually a lack of intelligence, it's a lack of information.
Section 1. The Flawed Mirror. Hidden Traps in Data.
You see, our expectation of perfect data pretty much always crashes headfirst into reality. Take survivorship bias, for instance. Imagine you're building an AI to predict startup success. You feed it data from famous unicorns, wildly well-funded startups, businesses that have already made it. Looks flawless, right? But you are only looking at the survivors. So your model gets tricked. It starts believing that massive funding simply guarantees success. It completely misses the scrappy little startups that suddenly take over the world, or the heavily funded ones that totally flop. The model didn't fail because the math was weak. It failed because we showed it a heavily distorted version of reality.
And man, it is so easy to fall into this next trap, sampling bias. Let's say you want to train an AI to truly understand emotional music. Naturally, you might grab a popular playlist called Top Hit Sad Songs. Makes total sense, right? Well, let's look at what actually happens to that data.
By relying on that specific playlist, your entire data set is automatically hijacked by popularity rankings, platform algorithms, and mainstream tastes. So your poor model learns that sad music literally just means popular slow songs by famous artists. It completely overlooks underground artists with deeply emotional tracks, or maybe fast-paced rock songs that actually carry heavy emotional weight. And this brings us to a really harsh reality in machine learning. The model didn't learn emotion. It learned your data collection method. At the end of the day, these models are basically just hyper-powerful pattern detectors. They perfectly reflect whatever flawed, biased mirror we hold up to them.
But hey, sometimes that mirror isn't just biased, it's completely shattered by noise. Let's imagine you're building a system to predict package delivery times. You feed it the data, but the real world is incredibly messy. We're talking missing timestamps, incorrect labels, tracking glitches, just chaos. The model tries to find patterns in that chaos. So instead of learning that distance and traffic affect delivery times, it might accidentally learn something crazy like, hey, deliveries on Tuesdays are way slower. Why? Just because some guy manually entered the wrong times on a random Tuesday. The intelligence gets completely corrupted by bad record keeping.
Section 2. Learning Disorders. When models learn wrong.
So what actually happens mathematically when algorithms try to learn from this kind of chaotic data? Well, say you want to predict if a student will pass an exam. You give the model their study hours and attendance, but you also throw in their favorite color, their shoe size, and the brand of their phone. Now, the model doesn't intuitively know what matters. It's going to try everything, and it might just spit out a fake pattern like, students with blue phones get better grades. I mean, absolutely absurd, right? But it happens. Not because it's true, but because randomness exists. If you feed a machine enough garbage, it's going to find a garbage pattern.
Here's another hilariously bad example. A model can literally learn something like, if a country's name contains the letter A, its happiness index is higher. It works mathematically only because the training data accidentally supported it, not because it's an actual real-world truth. And when a model embraces this level of randomness, oh boy, it triggers one of the absolute biggest pitfalls in all of machine learning.
And that pitfall is called overfitting. Think of it like a student prepping for a huge exam. Instead of actually learning the core concepts, they just memorize every single question in the textbook word for word. What happens on exam day? The professor changes the phrasing slightly and the student completely collapses. That is exactly what overfitting is in AI. The model memorizes the training data perfectly, but fails entirely in new situations.
Section 3. Taming the machine, the strict coach.
So you're probably wondering, how do engineers actually step in and fix these messy learning disorders? Well, they use a technique called regularization. Think of it like a really strict coach. The raw model is overeager. It wants to fit every single tiny detail, including all that noisy, irrelevant garbage data. But the coach steps in and says, whoa, stop overreacting. Focus on the main pattern. It essentially forces a kind of controlled ignorance. So instead of drawing a frantic, zigzagging line just to touch every single random data point, the model is forced to stay smoother and much simpler.
And honestly, this creates a brilliant balancing act. It's the ultimate Goldilocks problem. If your strategy is too flexible, you get overfitting. The model just memorizes the noise. But if that coach is way too strict, you get underfitting. What we are constantly searching for is that perfectly balanced middle ground. That's what leads to generalization, which is basically a fancy way of saying the model actually works in the real world.
Let's quickly flip the coin and look at underfitting. Imagine building a model to predict city traffic, but it only has one single rule: rush hour equals busy. Obviously, that is way too simple to capture reality. It completely ignores weather, holidays, car accidents, whatever. Because it didn't learn enough structure, it's gonna perform terribly right out of the gate. So who actually decides how strict or flexible the model gets to be? Well, you do, the human. While the internal patterns and weights are figured out by the machine, the overall complexity, basically how strict that coach is decided by human engineers. We call these hyperparameters. Think of them as the rules of the game that you set up before the game even begins, rather than the individual moves the machine makes while it's playing.
Section 4. Surviving the real world. Deployment shock.
Okay, so what happens when your pristine, perfectly balanced lab model finally meets the absolute chaos of reality? Honestly, it can crash and burn the second it goes into production. The real world is just relentless. Suddenly you're dealing with entirely different user behavior, massive scaling issues, crazy system limitations, and data that shifts over time. A model that is 100% accurate but takes 10 seconds to load? Yeah, that's completely useless in a real-time app. And a model that's super fast but unstable? That's actually dangerous.
So the absolutely crucial takeaway here is this. Machine learning is not just model building, it is system engineering. Surviving deployment isn't about having the coolest, most complex math. It's about building a robust, resilient system around that math to handle the shock of the real world. And because of this, we need to debunk a massive myth right here, right now. There is no universal ultimate algorithm. None. Sometimes a basic linear model will completely obliterate a deep neural network. Sometimes a really simple decision tree beats both of them. It depends entirely on the hidden structure of the specific data set you're working with.
This is exactly why the core philosophy of top, data-obsessed engineers is this. Success in ML is about understanding your data deeply, matching your model's complexity to the actual problem, and iterating intelligently. There's no magic bullet. There is only observation, adaptation, and human intelligence. So, here is your ultimate reality check. Whether it's an algorithm recommending your next video binge or routing your online orders, machine learning is not about teaching machines to think exactly like humans. It's really about shaping mathematical systems to behave reasonably in a world full of totally imperfect, biased, and noisy information. The hardest part literally isn't building the artificial intelligence. The hardest part is managing the human data.
I want to leave you with this final provocative thought. After seeing just how incredibly messy our data really is, are we truly teaching machines to think, or are we just beautifully shaping math to survive a really noisy world? Think about that the next time an algorithm tells you exactly what you want to watch. Thanks for joining me for this explainer, and keep learning.